This video is about combinations and compositions of trig functions. So we're going to look at a graph for these two functions, y equals sine x plus x squared and y equals x squared sine x squared. If we think about what might happen, sine of x, remember, is bounded between -1 and 1, and x squared grows pretty fast. So if we think about the first one, the x squared is probably going to be way more important than the sine. Whereas here, when x squared is multiplied by sine, the fact that sine changes from positive to negative every so often means that this graph is probably going to have a little bit more weight with the sine of x than graph number 1. And if we look at these graphs, what we do find is that number 1 essentially looks like y equals x squared. It's shifted over a little bit, and it's not perfectly a y equals x squared, but it basically follows the pattern of it kind of looks like a parabola, whereas number 2 looks a little crazier because your x squared function is getting multiplied by something that's between -1 and 1 and changing all of the time. So if I plug in, for example, 3 pi halves, sine of 3 pi halves is -1. But x squared, when x is 3 pi halves, that's 9 pi over 4. So it's 9 pi over 4 times -1. So that number, 9 pi, is 27, something like that. You end up with 27 divided by 4, and then that's negative. So it's going to be kind of a wild ride here. So what's going on is that the sign impacts the function differently based on whether it's multiplied or added or anything else. Now we're going to graph the function y equals 1/2 x plus sine x. If we think about what's happening, the graph of y equals 1/2 x would look something like this. And then sine of x, well, sine of 0 is 0. Sine of pi is also 0. So at pi, it's going to still be on the line. But essentially what's happening is as you're between 0 and pi, it's going to be a little bigger. And then from pi to 2 pi, it's going to be smaller. So kind of what's happening is your graph is going to look like the sine graph, except it's going to follow the line y equals 1/2 x. The next question is, what kinds of lines does it oscillate in between? And so if we think about what that is, this is the line y equals 1/2 x. What might happen? Well, sine of x is bounded between -1 and 1. So when sine of x is at its biggest, like at pi over 2 and at -3 pi over 2, this would be the line y equals 1/2 x plus 1. But when sine is at its smallest, this would be between, or the line y equals 1/2 x minus 1. So the equations of the two lines that oscillates in between are y equals 1/2 x plus 1 and y equals 1/2 x minus 1. And it basically just follows the line y equals 1/2 x going above and below it. So if you notice, the difference between problem 3 and problem 1 was that because x squared is a lot more powerful, the plus sine x doesn't really have as much of an impact. It impacts it a little bit, but the sine of x impacts this one a little bit more. You can see the wave, the sine curve going on. It just follows this line y equals 1/2 x. So this is still more important than the sine because, as you can see, it's following this line forever, and it's not staying between -1 and 1. But the amount that sine of x is important in problem 3 relative to problem 1 is pretty clear. The next topic that we're going to discuss are sinusoids, and they model sound waves and voltage in alternating electrical current and things like that. So sinusoids are things that look like sine or cosine graphs. And so one of the unique things about sinusoids is that there are some times when you can add and subtract sinusoids and they end up looking like another sinusoid. So you get another thing that looks like that. Sometimes you add them and it is still periodic, but it doesn't look like the typical sine or cosine wave. So what we're going to do is we're going to take a look at these two graphs, and we're going to figure out what that means in terms of how these graphs look. So if I look at 4 sine plus 3 cosine, what you see is you see something else that kind of looks like a sine wave. When you look at 2 sine 3x minus 4 cosine 2x, you see something that does not look like a sine wave, but it looks kind of cool, and it actually repeats itself over and over again. So what you see in these cases is you have the first one is periodic, so it repeats itself, and it's a sinusoid. Whereas the second one is periodic, but it is not a sinusoid. So once again, if we look at what this graph looks like, the first one, you see that it kind of looks like a sine graph, whereas the second one does repeat itself, but it doesn't look like a sine graph. So then the next thing that we have to do is, using the information gathered above, what guarantees a sinusoid? So it appears that if I add these two together, it works. If I add these two together, it doesn't. One other thing we may want to look at is, what about the graph of y equals 3 sine 2x plus 6 cosine 2x? So if we look at that graph, that also looks kind of like a sinusoid. It repeats itself, and so it's not only periodic, but it looks like a sine curve. And so this one is also a sinusoid. So in this case, what guarantees a sinusoid appears to be that the numbers on the inside, so the angles, have to be the same. So the periods of both of these things have to be identical. So notice that the period of this is pi. The period of both of these is 2 pi, whereas the periods of these are different. So because the periods of these are different, that means that even though it's periodic, it repeats itself in a different pattern, and so we end up with something that's not sinusoidal. So if we want to figure out what guarantees a sinusoid, if we add or subtract these things together, is that the periods of all the added functions must be the same. So if we look at these, we're going to decide if all 4 of these are not periodic, periodic only, or sinusoidal. And of course, if it's sinusoidal, it actually implies that it's periodic. So the first one, periods are the same. So we end up with a sinusoid. This one, not sinusoidal because the periods are different, but it is periodic. It repeats itself every so often. This one, same thing. Notice that the periods are not the same in these two. Number 8 is not periodic at all. And the reason it's not periodic at all is because, notice this is like a line that has a minus sine x. So we did something like that earlier up here. And that wasn't periodic because it grows as you get. It's following this line, y equals 1/2 x plus 1. This one would be following the line 1/2 x plus or minus 1 again. It's just going to shift around a little bit. So looking at the graphs just to confirm what's happening, we have periodic and sinusoidal. This one's just periodic. This one's just periodic, and this one is not periodic. Now let's talk about compositions. So if we try to graph each of these two things, let's look at what the Desmos graphs of these would be. And as we kind of look at them, what we see is that the function sine x squared means that we take y equals sine x and then we square it. Now we can also write that as sine squared x. You've seen that before. But notice that what happens is sine kind of would look like this. And so what ends up happening is everything that's a fraction or less than 1 goes in a little bit, right? Because, for example, when y equals 1/2, when we square that, it should be down to 1/4, right? So it dips down a little bit, but then 1 squared is 1. Then all the parts that are below the axis, when you square them, so for example, at 7 pi sixths, you end up at negative 1/2. That's going to, when it's squared, become positive 1/4. So it's a little lower, and it's also above the axis. Now, number 2, that's taking the function x squared, which looks something like this, and then taking the sine of each of those values. So what that's doing is it's taking numbers that can get huge, like for example, when x is pi, 3.14 or whatever. When x is pi, we're squaring that, so we end up with sine of pi squared. So notice that at pi, we're not at 0 anymore. That's because pi squared is not pi, it's 3.1 something times 3.1 something. So it's like a sine of 9.5 or whatever. And then we're plugging that into sine. So that's going to give us some value between negative 1 and 1. So what we see is that when we compose functions, it ends up being such that the order of the composition matters. Do each of these functions, when we look at them, do either of them appear to be even or odd? Well, remember that even functions are functions that reflect over the y-axis, and both of them appear to be even. The first one is periodic, and the period appears to be pi. The second one is not periodic, even though it is mirrored over the axis. It's not periodic because as you go on, you do not see the same pattern going over and over again. It actually gets tighter like an accordion as you move along. What about y equals sine cubed of x? If we show that graph, we end up with something that looks really cool, right? It is a composition of the functions g of x equals x cubed and h of x equals sine. And so the first thing that's happening is the sine, right? So it ends up being g of h of x. So we have g of sine of x. So you plug sine x into x cubed and you get sine of x cubed, which is the same thing as sine cubed x. So this is what's happening. So we're taking the function sine and then cubing all of those things. So again, it's never going to be bigger than negative 1 or 1 outside of that range. This function is going to be periodic. It's going to repeat itself every 2 pi. Notice that every 2 pi it appears to repeat itself. And the function is odd because if you rotate a point 180 degrees, you're going to end up getting a matching counterpart. So this function is odd, which makes sense because it's cubed. Now we're going to try to graph these functions by hand. So this one is cosine of x squared. So what we're going to do is we're going to look at the graph of cosine of x. So the graph kind of looks something like this. Then what we want to do is we want to square all of these values. So 1 squared is 1, so every time I hit 1 at negative 2 pi, 0, positive 2 pi, I end up at 1. At pi and negative pi, those were negative 1. When they get squared, I end up at positive 1. And then the same thing kind of happens. If I was at 1/2, when I get squared, I'm going to be at 1/4. And so my graph is going to look something like this, kind of like the sine squared graph did. So it's going to look very similar, except these peaks are going to be moved over a little bit. So notice that the peaks are at the pi's instead of the pi over 2's. This has a period of pi, and this function is even. Now, if we take a look at sine of absolute value of x, what's happening is you're taking the sine of the absolute value of x. So the first thing you look at is the absolute value of x, and then you take the sine of each of those things. So the absolute value of x looks like this. And so what ends up happening is, to the right of the y-axis, so when x is 0 or bigger, nothing changes about the graph of sine. So it's going to look something like this from 0 to 2 pi. And then over on the left side, instead of the function going down and continuing to look like this, everything's going to match whatever was on the right side. So your function is going to kind of look something like this. So this is an even function, but it is not periodic because we have some kind of weird exchange in the middle. Now, if I restrict the boundary, so if I restrict the domain to either being all positive numbers or all negative numbers, this is periodic over here, and it is periodic over here, but once I include both sides, this strange looking thing at the middle makes it so that it's not periodic once you cross the axis.